has the next question, if there are any, probably. Some of these are, trickier than others, but. So, I want to start by taking the derivative of both sides. When I take the derivative of the left-hand side, what do I need to use to do that? That's a chain rule, right? What's the outside function? Like e to the g of x, right? So the derivative of the outside function is just e to the whatever the inside function was. And then I have the derivative of the inside function. And we'll do that in a second. And when I do the right-hand side, the derivative of x is 1. And the derivative of y is d1 times dy dx. I'm not going to write the 1 time, so we're just going to write dy dx. So we'll go ahead and do the derivative of x over y now. To do that, it requires a quotient rule. So I have the bottom times the derivative of the top, which will just be 1, minus the top times the derivative of the bottom, which would be dy dx. And that's all over the bottom squared. So let's see. I got to get the dy dx is all on the same side. So let's start by just kind of distributing through that e to the x over y. And then I'll multiply both sides by y squared to get rid of the fraction. And so now I'll add the y squared dy dx to both sides to move it to the right-hand side. And I'll subtract the y e to the x over y from both sides so that I have only stuff with dy dx is on the left. So then all in one step, I'm going to factor out the dy dx and divide by the y squared minus x e to the x over y. I think that ought to do it. Giselle, does that feel?
Yeah, I just made like a little mistake in the
That's how little mistakes go in calculus, though, right?
Yeah.
It's punishing in that regard if you're trying to simplify something and you make like one little silly oopsie.
Yeah.
It's just like going back and finding and sometimes be rough. Sometimes it's better just start over. If you can't find it right away, sometimes that's just how it goes. What's next? Happy to do some more if others have any that you want to talk about. Chanel, is that a hand?
No, it's just there's something on my head.
Oh, okay.
On my head.
That's okay. I couldn't tell if that was like, I want to ask, but I'm not sure if I should.
No.
Okay. Usually you're not shy, so. Okay. If anybody changes their mind later, we can always circle back. But if you're happy, I'm happy. Today we're going to be talking about 3-6. We're going to talk about derivatives of logarithmic functions. So here I'm going to present you with a new derivative rule that the derivative of log base a of x is 1 over x times the natural log of a. Let's prove this rule. So let's say that we have the function y equals log base a of x. If I apply my definition of a logarithm, I could rewrite that as a to the y is equal to x. Everybody's okay there? If I do the derivative of both sides of that equation, what do I get when I do the derivative of a to the y?
A to like, isn't this one like Lin rule, the one that we learned?
This is an exponential function.
Yeah.
Yeah. So what is the derivative of this exponential function a to the y?
A to the y times ln of y?
The natural log of a
Do you put that dy?
times dy dx, yes, that we are doing an implicit differentiation because there's x and y's on both sides. And then the derivative of x is
1.
1. So if I get the dy dx by itself, I divide both sides by a to the y, natural log of a. And what is a to the y equal to? X. So I have 1 over x times the natural log of a.
It's actually not a very hard proof.
Not a very hard proof. The key was rewriting it as an exponential function and using our other derivative shortcuts, right? To do it. Yep. What will be an even easier proof is the one for specifically the natural log. So remember, the natural log is the same thing as log base e, right? So if I use the derivative rule from before, I should get 1 over x natural log of e. What's natural log of e?
1.
1. Even easier. These two derivative rules we've just shown you need to be memorized. So they're in the Quizlet already, but this will be the last of the derivative rules you see for the course. Mm-hmm.
Wow.
The rest of chapters 3 and 4 are going to be applications, and then we move to integration. Integration, which is the reverse of a derivative. Yeah, it's basically going backwards. How do you go undo a derivative?
Is that more difficult?
At this level, I think it's easier. In general, it's harder. But for what we're doing, I think it'll be easier.
Okay.
But we can talk in the future about why it's, I think, the harder problem.
Okay.
Okay, so let's go ahead and run through some examples. Just practice using this rule. So let's say we want to do the derivative of y equals the natural log of x cubed plus 1. Well, I do the derivative of both sides. When I differentiate y with respect to x, what do I get? Dy dx. To do the derivative of the natural log of x cubed plus 1, what do I need to use to do that? That's a chain rule. The outside function is the natural log. So the derivative of the outside is 1 over the insides. And then I have the derivative of the insides, which is going to be 3x squared So I'm done. That's not too bad, Mr. Kulik. Oh, not too bad. The book has these two additional derivative formulas. What are we really looking at here?
Isn't it just like implicit differentiation?
It's the previous derivative rule with the chain rule built into it.
Oh, okay.
So like your outer function here is like the natural log of x, and your inner function is u. So when I do the derivative of that, derivative of the outer, I have 1 over u times the derivative of u, which is du dx. It's just the chain rule combined into this rule. Do you need to memorize this? No, because you know the chain rule, and you'll know the logarithm rule, and we've been practicing over and over and over how to use the chain rule in conjunction with these other derivative rules. That's all this is saying. So I wanted to point this out to you, so if you're looking through the textbook and you see this thing, be like, we didn't learn this. Do I need to memorize this? It's like, you already know it. Okay. So let's do a couple more. Here we're going to do the derivative of the natural log of sine of x. To do that, what do we need to use? Chain rule. Good. What's the outside function? ln of x. So when I do the derivative of the outside, I get?
1 over sine x.
And then when I multiply by the derivative of the inside, I have? Cosine x. And cosine over sine is?
No, it's cotangent.
Cotangent. Good. So far, so good. Okay. Again, when we said this was going to be kind of an easy lesson, it's not too bad, right? How about this one? The square root of the natural log of x.
Chain rule?
Chain rule again. What's the outside?
Square root of x.
Square root of x. So the derivative of that is?
Half x to the negative half.
Yeah, half inside to the negative half.
Yeah.
And then the derivative of the inside is?
1 over x.
Yeah.
So we could just write this as 1 over 2x square root natural log x. Is okay there? So far, so good? Let's do another. And we have log base 10 of 2 plus sine x. Again, to do this, what do we need? Chain rule. So the derivative of the outside is log 10 of x. So when I do the derivative of the outside, I have 1 over the inside times the natural log of 10. And then I have times the derivative of the inside, which would be?
2 plus, yeah.
Cosine x.
0 plus cosine x, or just cosine x. How about this one? First, though,
Oh, it's a chain rule.
chain rule,
Quotient rule inside the chain.
and then inside of the quotient rule is
Chain rule.
another chain rule. Ugh. Guess what? It's an easier way to do it than that. Who remembers their properties of logarithms from pre-calculus or algebra 2? There are 3. There's the quotient property, where if you have the log of a quotient, you can write that as a difference of 2 logs. There's the product, oops, where if you have the log of a product, you can write it as the sum of two logs. And then there's the power property, where if you have log of something to a power, that power can become a coefficient. Yes?
I'm so sorry, but I think I left my phone in Miss Elwood's classroom. Do you mind if I go grab it?
No, it's okay.
I'm so sorry.
It's okay. No biggie. Everybody okay remembering these now that I wrote them down? Sure, says Giselle. You know, it's okay. So what we can do is, what if we take this natural log of ugly thing and we expand that logarithm like we would have done in pre-calculus or algebra 2? If we do that, we're going to end up with just two chain rules. So expanding, remember, we want to go quotient and then product and then power. So do I have a quotient property going on here?
Yes.
Yes. How would I write it?
1x plus 1 minus 1 root x minus 2.
Mm-hmm. Everybody's good there? So we did that. Do we have a product property?
No.
No, there's nothing being multiplied together. Do we have a power property?
The root.
Good. Remember, we can treat that square root as a exponent of 1/2. So we can do that. What we'll do then is let's differentiate this. Doesn't that look a lot nicer to do the derivative of? So when I do the derivative of the natural log of x plus 1, what do I get there? Good. So I have 1 over x plus 1, but it's a chain rule, so I also have times the derivative of the inside, which is just the derivative of x plus 1, so 1. And then when I do the natural log of negative 1/2 of natural log x minus 2, I'll just have the negative 1/2 times the derivative of the outside, which is 1 over the inside, times the derivative of the inside, which is again 1. And I think that's probably good enough. In the textbook, they might make a common denominator or something, but I'm okay with that answer. Everybody feels okay?
Yeah.
That seemed a lot easier than trying to grind through a chain rule with a quotient inside of it, with a chain inside of that. Right? So let's look at when we take the derivative of the natural log of x, or the absolute value, the natural log of the absolute value of x. Why do we still just get 1 over x?
Can't take natural log of a negative thing.
Or a 0.
Yeah.
But if that's the case, then the natural log of the absolute value of x is still just going to be the same as the natural log of x, provided that x is greater than 0. So it's just the same thing, right?
Yeah.
Well, that's nice. All right. What about something like this? I watched Katie's eyes get wide when she looked at that. I was like, oh no. What's going on in this one?
Products.
First is the quotient,
Oh, quotient rule.
and then inside of the quotient rule we have a product rule,
Times
and
the
inside of the quotient rule, or inside the product rule, we have
chain.
a chain rule, and inside of the quotient we're going to have another chain rule. Yo, brother, where art thou? That's going to be a nightmare, right? But what if there's an easier way?
Is there?
What if there's an easier way than grinding through all of that? Now, what we can do here is that was going to be a lot of hard calculus, right? Because of the nesting of those rules. What if we could change this into just 3 unlinked chain rules, but you might have some gross algebra at the end? Does that feel like a good deal?
Yeah.
The chain rules will be really easy chain rules.
Okay, it's just because algebra is just like, it's hard to sometimes.
So here's the trick if you want to go this route. What if I start by taking the natural log of both sides? That's okay to do, right? Because I did it to both sides.
Sorry.
That's okay, Eva. Then we can apply, or we can expand that logarithm on the right-hand side, correct? Which property would I apply first?
The quotient property?
Mm-hmm.
The natural log.
And then I would apply product property, which I see inside the first logarithm. And then I can do the power properties. Everybody feel okay to hear on how I've expanded things? Now let's take the derivative of both sides. What do I get when I take the derivative of the natural log of y? I get 1 over y times dy dx, right? And what do I get when I do the derivative of 3/4 natural log of x? What do I get when I do the derivative of 3/4 times the natural log of x?
Good. 3 over 4x.
Okay, 3/4 times 1 over x, or 3 over 4x. That's good. What do we get when we do the derivative of 1/2 natural log of x squared plus 1?
1 over 2x squared plus 2.
1/2 times 1 over x squared plus 1 times 2x. Right, we have the derivative of the outside times the derivative of the inside.
Oh.
And then the 1/2 just pulled out front, right? Okay. How about the next one? Oops. What's the derivative of the last chunk there?
5 times 1 over 3x plus 2 times 3.
Good. So if I simplify this a little, or combine some like terms a little bit, notice the 2's here are going to cancel. Right? And then I'm going to multiply both sides by y to get the dy dx by itself. And then what does y equal? Oops. What does y equal? It's the starting problem.
Oh, got it. Thank you.
Mm-hmm. Now, at this point, to simplify this all the way down would require you to make a common denominator here and combine your like terms, and then you just multiply the two fractions together. I'm not going to do that right now. But if this was just a free response question, the answer that we've provided here is okay, right? The calculus is done. The dy dx is by itself. You don't need to clean that up any further. That would be acceptable to stop at. If it was a multiple choice question, I might not choose this route because the algebra cleanup can become kind of taxing. It might be easier to try to run through the hard calculus or not. Depends on how confident, where your confidence lies. Do you feel better about doing your algebra quickly or your calculus quickly? I might even opt to do this algebraically because it doesn't feel like it's going to be, like it'll be stinky but not super stinky. Because to make a common denominator, I just have to FOIL in one spot. Everything else will just be distributing, which won't be super, super bad. And I suspect there won't be anything left to cancel. So it'll just be like me tacking whatever that yellow thing is next to the things in the not highlighted piece and being done with it. Does that feel okay? So that technique I just showed you is called logarithmic differentiation. So the steps that we used there is we took the natural log of both sides of our equation and expanded the logarithm. We then did like an implicit differentiation to take the derivative of both sides, and then we separated the dy dx by itself. And I guess here I had illusions of doing this problem both ways. I'm not going to do it the hard derivative way just because it feels like you got the point of it, of what we did here, right? I'm just going to do it the logarithmic differentiation way that we just did and not do it the old way, which again, still doable, but like, kind of rough, right? If I call this F, G, and H, this is going to be H times the derivative of FG minus FG times the derivative of H over H squared. And that's going to be H times F times the derivative of G plus the derivative of F times G. And then to do the derivative of H, and to do the derivative of g both require chain rules, and to do that. But that's kind of the way you'd set that up. And you can see right away that like the calculus is going to get kind of gross, right? I think that's probably enough illustration of like where you would want to go with this, right? But again, you can do it either way. It doesn't matter to me which way you approach the problem. On the homeworks and in free response settings, you don't need to worry about simplifying it down, right? Now you should still practice doing that, because on a multiple choice question, you won't have the luxury of just stopping when the calculus is done, unless you're able to like eliminate which of the multiple choice answers can't possibly be correct from what you have. But sometimes that can be quite difficult to tell. I have one more example, and then we are donezos. What if I want to do the derivative of y equals x to the square root x? How do I do that? Y equals x to the square root x. Let's differentiate that. How do I do that? Well, what's the outer function?
Oh, x to the x.
That's not one that we know a rule for.
I don't
Would you do power rule?
Where's the power rule? That's like x to the constant.
Oh, you have to take by like the logarithm.
I have to do this using logarithmic differentiation. There is no other way. So that's right, we do need to do the log of both sides. Because when we apply our power property for logarithms, it becomes that. Now if I do the derivative of both sides, the derivative of the natural log of y is 1 over y dy dx. To do the derivative of square root x times the natural log of x requires a product property. So when I multiply square root of x times 1 over x, how does that reduce?
x to the negative half.
Yeah, I'll write it that way, but that's okay. And then here I have natural log x over 2 square root x. So I'll just make a common denominator. That looks pretty good to me. Oh, not yet though. Why not, Mr. Kulik? Yeah, we got to get the dy dx by itself. There we go. So that,
What did you multiply by x to the root x? Sorry. Oh, because keep forgetting that.
that's what y is.
So you can't just do times y. You have to input that specific function.
Yeah, because unless it's telling you to use implicit differentiation, dy dx should be only in terms of x's.
Okay, got it. So for the previous lesson, we didn't do that because it said implicit differentiation.
Yes. If we look at the directions on, oops, let me do this. Oh, come on, computer. See, dy dx by implicit differentiation. If you have that in your instruction, you're welcome to leave x and y in your derivative. That's okay. But if it just says find dy dx or find the derivative or find f prime or y prime, should not have anything other than x's.
Okay, got it. Thank you.
So it's a directions thing.
Okay.
Let me see. I did not get to do that. Hold on. Let me get the problem set here. So your problem set for 3-6 is this. We have 2 sections left. I think they're the easiest 2 sections in this block of sections. Yeah,
Are we doing one on Thursday, one on Monday?
that's the plan.
Okay.
Depending on how you guys feel, we could do them both on one day and take a free day. I think is realistic, but we'll talk about that on Thursday and see how you feel.
Okay.
So 3-7 is just like application problems, just kind of like story problems where you have to take derivatives and solve stuff with derivatives. You know, things we've already kind of done before. And 3-10 sounds scary. The notation in the textbook is terrible, but it basically just boils down to writing tangent lines and then using the tangent line formula to make an approximation. So like plugging an x back into the tangent line and getting a value to come out of it,
That's pretty easy.
which is something, again, we're familiar with. We've done lots of tangent lines. That's something we should feel pretty comfortable doing. That's it. Those are the last 2 topics here. You know, like 3-7 is, you know, something like this. Position function, you know, find the velocity, blah, 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 blah. Things that we've already kind of done. And then this is, like the notation looks scary, but that's just the equation for a line. That's all you're really doing. Because the idea is that if you use a line, you write your tangent line. If you look at x's quite near the x, the tangent line gives you a pretty good approximation for the y values for x's that are close to your point of interest. That's the idea. You just write a tangent line and then you can use it to approximate for x's near by. That's the whole idea. Look at that, it took like 2 seconds to kind of give you the rundown. We could definitely do both those sections in a day if you would rather do that and then have an extra free day to work on problems or whatever. It's up to you guys. Should have, by next class, I should have like a test description done for you. I've been kind of working on it. If you've looked at the testing, you might have seen me typing things in there. Hasn't finalized yet. And have a multiple choice and free response question set in there. Did you like it when I just published those as a PDF and dropped them into OneNote? Was that more convenient than going through the MyAP site?
Yes, that was way more convenient,
Yeah.
Okay.
actually.
I'll just keep doing that then for these big reviews.
Yeah.
I'll put it as an assignment there also, but feel free to just,
My IP was really slow. In like,
it can be very laggy and like droppy.
Yeah.
Yeah.
PDF was regular. It was easy to sign into. Like you just open up your laptop OneNote and then put OneNote. But my IP, you have to go through all of these. Like,
Yes, they do make you do a million screens to get to where you want to go.
Yeah.
So I will do that then for you guys again. I just figured out how to do that. I didn't know how to like publish that quiz as a PDF yet or before. So
Is Isn't like last unit, like the MyAP was like, is like a good study to study scores for this test?
Well, here's the thing: is there are things that we haven't done that would be in the the unit reviews, which is why I've just been like, I'm just going to make you a big. Mr. Gulick picked these questions intentionally.
Okay.
But because I know that for the first test I did that, and I'm just like, oh yeah, we have to skip this one and that one, and because there was stuff we hadn't done yet.
Yeah.
Because the MyAP's units are different than your textbook's units.
Okay.
So like a lot of times you're overlapping like
Ideas.
yeah, that are in our textbook that aren't in the AP thing yet, or that are in the AP thing that aren't in our textbook yet. So I just went and basically made my own, right? Like here's a billion questions, but I can look through those too and see if there's anything good in there.
Okay, I'm in terms of for your test, is
Yeah.
it pretty good? So you scores the last test.
I built everything kind of the same way. So if
Okay.
you felt like what you did last time was good
Yeah.
preparation for the test, I would,
Do the same thing.
yeah.
Okay.
Because I built the test kind of the same way. So I did it
Okay. Perfect.
very much, in the style of AP questions, and just, some things I stole exactly. Some of you might have noticed like, hey, I remember doing this exact question. And some of them might have been like, we did something like this, but this is, like the numbers and stuff are a little different or whatever.
Yeah. I liked that a lot. Yeah, just having a set.
Yeah.
Kind of thing.
And there was enough of them that
You got enough practice.
yeah, you had to really grind through all of them to and some of them were just all kind of the same.
Yeah, I noticed that.
But it was like, okay,
This is good practice.
Yeah.
I like that.
yeah. But yeah, I built the test again very similar to what I did the last one. So whatever you did last time should be fair preparation. If you felt underprepared for things, then that should tell you okay, I need to do a little bit more on this or that or whatever.
Okay.
Nolan?
This is just kind of random, but
Okay.
what do you do if you can do a chain rule if it's 5 to the x, right?
Mm-hmm. Well, that's not even really a chain rule. That's just a straight exponential.
Lynn type of problem? It would be
So where was it? It was here. Right? 5 to the x is just 5 to the x times the natural log of x, or natural log of 5. So that's all you need. You don't even really need a chain rule to do that.
What if there was a problem with 3.4 though? It was 5
Right.
negative 1 over x.
This is the 3 point.
Oh, so 3.4.
Yeah. Oh, if it was 5 to the negative, what was it?
5 to the negative 1 over x.
5 to the negative 1 over x. I think they probably would have expected you to think about it this way.
okay. I'm Chanel. Okay.
And do that and use your exponent rules to kind of wiggle your way through it. But this is a chain rule. 3-4 is the chain rule section.
Oh.
So you could have done it using the chain rule also, but
But I don't want to go. Just
I think that should give you the same thing.
didn't it just say 10:30? Am I going nuts? I think I'm going nuts.
It wouldn't be the first time.
Go to the bathroom.
Yeah, take your walk.
Thank you.
You're welcome.
Mr. Goulet,
Yeah,
can I just go back to Miss Elwood's room? She wasn't there before, and I need my phone. And
that's fine.
so,
Sure, you can check again.
Thank you.
No problem.